Well, hello everybody, Dave here, and today we begin our lessons on electric circuits. We'll talk about the various variables that are at play when it comes to an electric circuit and how they're all related together in one nice mathematical equation known as Ohm's law. So we start off by describing what it actually is. There's a diagram in the bottom there that shows you the three basic properties of every circuit. The first is an energy source, in this case it's a battery. The second is a closed path. You'll notice that the wire starts on one end of the battery and goes all the way around to the other side of the battery. And the third thing is some device to use up some of this energy. In this case we have a light bulb. If any one of these three things are missing, then we don't actually have a defined circuit. So first let's talk about the power supply of the circuit itself. In this case it's going to be a battery. Now when you take a look at a battery, there are essentially three elements that exist in a battery. You'll notice that the battery has positive charges on the top and negative charges on the bottom. If you've looked at a battery before, you'll actually see that these are labeled on the side as positive and negative. And what these are, the cathode, which is positive, and the anode, which is negative. And inside a battery, if you've ever cut one open before, which I highly do not recommend, there's actually this fluid in there because that's an electrolyte. And the electrolyte is going to be important because it's actually going to help the battery do what it's supposed to do. And so basically what happens is the chemical reactions in the battery cause a buildup of electrons at the anode, which is the bottom part of the battery. Well, this results in an electrical difference between the anode and cathode. If you've studied any electrostatics before, you know that if there is this potential difference, the result is going to be some kind of motion of these charges. And so the electrons want to rearrange themselves to get rid of this difference. They don't like being separated. They want to be random. And what happens is the electrolyte actually keeps the electrons from going back up towards the anode. Well, the only way that the electrons have now to rearrange themselves is to flow out the end of the battery and into the circuit itself. And so if you take a look at this diagram, what's actually happening are these electrons are actually flowing through the wire around back to getting to the cathode. What happens inside the battery is once those electrons get there, the electrolytes will literally push them through the battery until they get to the anode yet again. And this is the process that continues. One of the visuals that I like to think of when I think of a battery is a charge escalator, that when those electrons get to the cathode side, it almost works like an escalator to push that charge back to the other side so that it can flow through the circuit again. So you'll also notice on a battery that there is this label of a voltage. In most cases, at least with AA and a D battery, you're going to see a 1.5 volt listing. Well, this is actually the maximum potential difference that that particular battery can have. And we give that a special name. We call that the electromotive force, or the EMF. Now, please don't be confused by the word force in this case. It's not actually a force at all. But what it means is the voltage of the battery, the ideal voltage of the battery. If you actually hooked up a battery to a circuit and measured its voltage, you wouldn't actually read 1.5 volts. And that's because all power supplies have a little bit of internal resistance inside them, which means that some of the energy associated with the battery is actually being used up inside the battery itself. So the real voltage of the battery may be more like 1.3 or 1.4. So we'll get into that a little later when we talk about power. Now, you can think about circuits in the same way that you think about flowing water. And you can see that we have a diagram here that's a pump. And what's going to happen with that pump is it's going to push the water through. The water is going to flow through the pipe, and it's going to get to whatever vessel is on the other side. Now, you can think of the pump like the power supply. So you can see that the diagram below has a battery where the pump is. And what the battery's job is literally to pump the electrons through the circuit. And so what happens is if we have the water flowing through, if we pick a point along that pipe and measure the rate at which the water is flowing through that point, now we can get the flow rate of that water. Well, in the same regard, when we do that with an electric circuit, we can actually measure the amount of charge that passes by a given point in a given amount of time, and that amount of charge per second is called the current. So current by definition then is the rate at which an amount of charge flows by a given point on a wire. If you look at the bottom right, you see a diagram there, and you can imagine that we've taken a wire and we've cut it straight across. Well, if you look at the end of the wire, what you would see is this piece of area that we have diagrammed there. Well, the current then is the amount of charge that flows through that area and the amount of time that it takes to do so. So I is equal to delta Q over delta T, where delta Q is actually the total charge. The units for current are coulombs per second, or amps. If these are individual particles, then we just have to know the number of particles that pass by times the charge of each particle. And regardless of if they were protons or electrons, the charge would be the elementary charge, which is 1.6 times 10 to the minus 19 coulombs. Now, with circuits, we always deal with conventional current. And what that means is, when we first understood electricity, we didn't actually know that it was electrons that were moving through the wires. So we just assumed that they were positive charges. And so all of the textbooks will use conventional current in its direction of the current flow. However, we learned later on in life that it's actually electrons that are flowing through the circuit, and so the electron flow would actually be in the opposite direction of what the conventional current flow is. For all questions involving circuits, we're going to go ahead and stick to conventional current, but recognize the fact that it's actually electrons flowing through the circuit. Now, a common misconception about electrons flowing through the circuit is that they do so at near the speed of light. This is absolutely not true. Further on in a course, you're going to find out that these actually move quite slowly according to a quantity known as the drift speed. Because what's happening is there's actually collisions taking place through the wire, which is being used as a conductor. And what's happened is the power supply has produced an electric field within this conductor, which is causing the actual flow of the particles. Well, that's why a circuit works instantaneously, is because as soon as the power supply turns on, now we have this electric field in the circuit so that the charges instantly move. At the same time, they are moving incredibly slow. They're moving somewhere around 1/10 of a meter per second. So we're not talking about a very fast speed because of all of the random collisions that have to take place for these particles to move. So when we think of current, don't think of near speed of light traveling. Think of this massive amount of collisions taking place caused by an electric field in the conductor, which is causing the overall current to move through the system. Now, there are two types of current that can be studied. The first is direct current, and this is the circuit that we've already looked at. We have a power supply, we have a flow of electrons coming out of the anode, and you see that the electrons are moving in the same direction the whole way around the loop. That is what direct current means. If you take a look at current versus time, the graph, you can see that it's this nice horizontal function because it never changes direction. That's different from alternating current, where from a power plant, we can begin with current going in one direction, and then we have current going the other direction. And what you see with a graph of current versus time is this sinusoidal function where we go one direction, then the opposite direction, then one direction, then the opposite direction. Now, you may recognize alternating current as the type of current that powers your house. And there's an interesting historical story behind the feud between allowing direct current to power your house and alternating current to power your house. And it came down to three names, specifically Thomas Edison, George Westinghouse, and Nikola Tesla. And as the story goes, Thomas Edison was trying to create systems that allowed houses to be powered by direct current. The problem with direct current, though, was that you had to have power plants awfully close to the houses that were powering them because of the immense losses that occurred in transmitting the power from the power plant to the house. The result was we had a lot more power being sent to our house than we needed, and that is far more dangerous to the folks living inside. Well, George Westinghouse, and later with Nikola Tesla, actually worked on this alternating current idea with some knowledge of electromagnetism. And the idea that with alternating current, they could apply this concept known as transformation, which actually allowed high voltage to be transmitted at very low current. The result is a far smaller amount of power loss which allowed for the power plants to be much farther away from the houses that they were powering. From there, a transformer could actually take that high voltage and step it down to a more manageable voltage within the house, which was far less dangerous to the people inside. Though there was a significant resistance from Thomas Edison, inevitably, as we know today, alternating current won out. So now we can talk about the last quantity that plays a key role in circuits, and it's this idea of resistance. And we've all heard of resistance before. Well, physically, the definition is that there are these collisions that are taking place inside an electronic device. And the electrons that are coming into this device are colliding with the actual conduction material, and the result is there is this energy loss due to these collisions in the form of thermal energy. If you've ever put your hand over a resistor or touched a resistor, you'll notice that they're exceptionally hot. And it is because of this use of energy that's so important. If we go back to our analogy of a circuit being like flowing water, then resistance is some debris inside that flow that's causing the water to run through it. It's still going to flow through, but it's obviously going to have an interaction with that debris that needs to be considered. This is very much similar to the collisions that are occurring inside a resistor because it's inhibiting the movement of charges in very much the same way as the force of friction would in the case of the water flowing through the debris. Now, the unit of resistance is called the ohm. So there is a law that actually combines these three variables together, and it's known as Ohm's law. And Ohm's law, by definition, states that the voltage is directly related to the current when the resistance is constant. It's important to recognize that resistance is going to be constant in this case because, as you'll find out later on in studies, resistance can actually change over time as temperature will affect the overall resistance of a material. So we are always going to assume this to be constant. Now, if you look at the mathematics on the left here, we've made the statement that the potential difference is proportional to the current. Well, if we take a look at a graph of voltage versus current, that looks decidedly linear. And based upon this proportionality, we can actually determine that the slope of this graph is indeed the resistance of the circuit. And so we end up with the equation known as Ohm's law of V is equal to IR. Now, this is a bit of a misnomer because this implies that voltage is what causes current. But as we've discussed in this lesson, that's absolutely not true. So if you want to write this law in a more physically meaningful way, then you should actually write it as I is equal to delta V over R, because it is in fact the potential difference and the resistance that can cause the current for the circuit. Conventionally, however, you're going to see it as V is equal to IR. You'll notice that we've also written it in terms of the EMF. Again, depending upon the question, it could be the EMF, it could be the terminal voltage, it could be delta V. For the most part, they're all going to mean the same thing. So with an understanding of electric circuits, we were able to create a circuit that allowed us to power our homes the way we know today. The basic idea behind this is demonstrated in the diagram below. We have a power plant, and an example of a power plant in British Columbia would be a hydroelectric dam. And a hydroelectric dam incorporates the movement of water through a turbine, and the spinning of this turbine combined with some understanding of electromagnetism allows us to generate electricity. So the question became, how do we get the electricity from the power plant to our house? And the answer came down to Ohm's law, an understanding that if we have an exceptionally high voltage traveling through a line at exceptionally low current, the result is going to be far less power loss as it moves from the power plant to the power substation and inevitably to our homes. Now you'll notice that at the substation and just before our home, we have this transformer. And again, this is a concept in electromagnetism where we have a voltage coming in. It is then stepped down in voltage using a process of induction, and that new voltage is then transmitted down the smaller power lines until it gets to the transformer by our house, stepped down in voltage yet again to the voltage that can be used in our house. So this idea of a step down and step up transformer is a concept that is studied in electromagnetism, which will be a topic that you'll deal with at a later date. if you ever look at the power meter of your house, you'll notice that it reads it in terms of these kWh's, which represents kilowatt hours. And the definition of that is the energy consumed in 1 hour at a constant rate of 1 kilowatt. And so this is energy consumption, and you can relate it to joules in the following conversion, that 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. So when dealing with power in our basic circuits, we have to go back to how charges are moving to begin with. So we have the chemical energy associated with the battery. And inside this battery, we're going to have these electrons, and these electrons are going to gain electric potential energy because of the mechanism of the battery itself. We understand from conservation of energy that this electric potential energy is going to be converted into kinetic energy as the electron travels through the battery. The equation that you see before you is the electrostatic equation for work, which is equal to the change in potential energy, which is equal to the charge of the particle times the potential difference between the anode and the cathode. Again, if you've never heard of that before, you just haven't studied electrostatics yet. So with this kinetic energy, the electron will now flow through the circuit until it reaches a digital device like a resistor. And what will happen, as we stated before, is that there will be collisions that take place inside this conductor, and the result is going to be an energy loss by the electrons because it will be gained by this digital device in the form of thermal energy. So if we assume that there's no energy loss in the wires, which is something that you will always do with basic circuits, then we can actually determine the amount of energy per unit time that is used by this device. So if we take our equation for energy, which is equal to Q delta V, and we relate this with respect to our time delta T, well, now we've actually created an equation for power, because power by definition is the amount of work per unit time, which in this case is the amount of energy used per unit time. And so we also know that delta Q over delta T has been defined as current. And so what we end up with here is a nice equation for power in terms of circuit quantities I and V. So P is equal to I delta V. If you remember from previous study of power, the unit of power is a watt, which is also a joule per second. So I talked about this when we were discussing Ohm's law, but it's important to recognize that for these problems, we are going to assume that a material is ohmic, in that it will be a constant resistance no matter how long the circuit is turned on. If something is non-ohmic, that just means that the resistance is going to change with respect to time. And this is where, again, in future studies, you'll find out things like temperature play a role into what the actual resistance of a given device is. So when we take a look at P is equal to I delta V, if we assume that something is ohmic, then we can apply Ohm's law to get two additional equations to represent power in terms of voltage and resistance and in terms of current and resistance. And again, the big disclaimer I have to give you when you use these equations is you absolutely only use them if we know that the material is ohmic. If it makes no statement about something being ohmic or non-ohmic, you absolutely will assume that it is considered ohmic. So that does it for this lesson, everybody. I hope everybody understood something to do with these variables and Ohm's law, and best of luck on your practice problems. We'll see you again.